What in your mind is the most valuable idea on planet Earth right now?
Oh, that is a good one. I think it is something like gradient descent. That is, there are many things that you can improve. And if you have a way of measuring how good something is, and you try things, you can find a rough direction of improvement. This doesn't always work for all problems. There are some problems that are impossible to get out of, but there are a surprising number of them that can be fixed. And it's a very powerful tool, especially in machine learning, obviously, but also in improving one's life. Try things, see what works, try to see the pattern, and then you can use that pattern to direct what you're doing.
Again, an absolute honor to have you here, Professor.
Well,
So I
thank you
thought
for
we'd
having
start.
me.
So I thought we'd start off where you started off life in Sweden. And I wanted to understand a little bit about how sort of Swedish culture and your early upbringing sort of gauged your interests into science and philosophy.
So I grew up here in Sweden and in the 1970s. So this was in the middle of the Cold War, and Sweden was also at the height of the People's Home, the program to build the welfare state. And I grew up in one of the northern suburbs of Stockholm, Hagalund, which got a bit of a reputation, but it's kind of dominated by big blue high-rise buildings, very affordable, very well built. It was kind of an epitome of let's make a rational, effective society. And it was pretty boring. So as a kid, I was reading all the science fiction novels at the local library and started to dream about, well, what about a world which wasn't all about concrete and getting a sensible job and doing sensible things? What about the universe? What about grandiose space battles and the meaning of it all? And gradually I realized, maybe I could make that real. Maybe I could actually build spacecraft. I vividly remember being about 7 years old. I spent a day drawing this enormous spacecraft, a solar sail-based city spacecraft that was kind of intended to get to the stars. And then I had this moment where I realized I have no clue whether this could actually fly. I had that disquieting realization, probably not. Probably absolutely not, but I didn't even know why. And then I had this realization, that's probably some math thing. I probably need to learn math and physics and stuff. So that's where I started devouring that part of the library. So in order to figure out what does it take to make a spacecraft that can fly? Okay, let's read all the physics books, the chemistry books. And once I was done with the local branch library, I ended up going to the municipal library about a mile away. And then I started devouring that. And eventually I went into the Stockholm City Library and kind of kept on going.
I mean, that's as every child does it, right? That's a fascinating sort of plot for how you reached there. I'm wondering, did you grew up in the 80s, which is a pretty seminal time in terms of science and technology, and I'm guessing you moved into your adolescence at the end of the 80s, roughly. Um, was there anything in specific in terms of sort of science and technology of that era that sparked your curiosity? I mean, I can imagine from an early age you've had quite the curiosity.
Oh yeah. So these stories about the spacecraft, etc., that began in the 70s. But in the 80s, of course, I encountered the computer. So I already had some brief interaction with computers back in the late 70s. There was a debate in Sweden where there was this realization that computing is becoming more and more important. Maybe we need to have ways of handling that. So there was some big exhibitions at the Museum of Technology, and there was new laws about management of privacy of databases. So there was this debate about computers and what we could do. So there was newspaper articles, and I was, of course, devouring that too. And then I got a chance to actually play around with a computer early on, maybe 1980 or so. That was awesome. But mostly, of course, I encountered computing in form of what I could read in the books. So I wrote pieces of paper with the basic programs on them. And eventually my parents got fed up with that. So they bought me a Sinclair ZX81 computer in 1981. So this is a computer that had 1 kilobyte of memory. You connected it to the television set. It had 44 times 60 pixels resolution in black and white. And I had to stop programming around 5 in the afternoon because that's where state television turned on the transmissions for television programs. And that tended to interfere with what I saw on the screen. So yeah, I was kind of forced to not work on computing in the late evenings.
One kilobyte. I can't even imagine. Sort of is and that's extendable hardware. Is that a floppy drive? What is that?
So that was the built-in RAM memory. Now I very quickly got an extension to 16 kilobytes. And still, I mean, by today's standards, this is of course where I can totally launch into kids of today think a gigabyte is not much, etc. But it is a really good exercise of figuring out how do I program if I only have a kilobyte? How do I make my program more effective? And of course, some of my friends, they had parents that were a bit well off or and had given them computers like the Commodore 64. I mean, 64 kilobytes of RAM, that's enormous. But I learned a lot by trying to program within these constraints. And I think it made me actually a pretty decent programmer. You could argue, I think, as many modern programmers would do, that actually, Anders, you're not a great programmer because saving memory is not that important if you have entire cloud to put stuff in. It might actually be useful if you're trying to make something like the computer for a space probe, but not really for an app on the phone. That's a supercomputer that doesn't have memory and processing limitation in the same way. But I do think you learn a lot of things by working within a lot of constraints. So I think that's healthy. In high school, my computing teacher, he was actually a real hardcore guy. He had been part of a team that built the first Swedish computer in the 1950s. And he was limping a little bit. The reason was he had once dropped a bite on his foot. So they had these big racks of vacuum tube electronics back in the 50s. And well, they broke all the time. So his job as a junior member of the team was to replace broken vacuum tubes. And when he pulled out one of the drawers corresponding to 1 byte of memory, he drew it out too far. It fell on his foot and crushed it. Fortunately for him, this was a Swedish byte. At the time, that was 5 bits. Not 8 bits, that's the British standard, which eventually became dominant. But the cool part was in high school, he was teaching me a bit about machine code in this ancient computer. And most of my classmates were groaning about the irrelevance of this. I mean, why do you care about a computer that's been kind of dead and disassembled for decades? But the beauty is, of course, now you understand some of the deep cores. And then you're very thankful that today we can program in advanced language. We don't need to think about the assembly language. But at the same time, I think it's important to recognize the entire technology stack. We are dependent on a lot of these technologies. And if we ever need to rebuild computing, we need to remember how to make good machine code, how to make the digital circuits work, and then do that so we can quickly forget about the darn thing because it's way too much hard work.
Right, right. Keeping track of the past is very synonymous to sort of dependency management for us programmers. I mean, it's
Yeah.
sort of it's like it's like a prehistoric sort of conceptualization of the past, thinking about like Fortran and these programming languages to people my age that are just these are like, sort of dinosaur age programs.
Yeah,
It's
and
fascinating.
I'm proud that I never learned how to program Fortran. I just barely managed to avoid that. So when I went to
Wow.
university in the early 90s, uh, of course, we started out by learning how to program Lisp, which is, of course, older than even computers. It's kind of like the Latin or French of computing. It's beautiful. It's slightly old-fashioned, but very elegant. And then, of course, we were writing in C, not C++. This was raw C back in the day. And then we learned a lot of other languages. But I managed to avoid just barely having to learn Fortran because it's a pretty horrifying language. It's a mess. But since so much has been written in that, so many pieces of really important scientific code, yeah, they're still just being updated. They're still around there somewhere. So there's certainly a market for Fortran programmers, just like the poor COBOL programmers. Some of these dependencies are just too expensive to ever get rid of, which is A very sad truth, but also kind of useful to know that sometimes you need to have those dusty manuals around.
Hopefully the novice sort of indie artists that enjoy going back into the past and playing around with these things can keep them alive. So that's
Yeah.
interesting. And then you moved on to Stockholm University, if I'm correct. Is that where you pursued an undergrad, moved out and did your PhD as well in computational neuroscience, or how did that track go?
Yeah, so I had this problem that I was interested in all kinds of science. By this point, I was still reading a lot of science fiction, but I wanted to do everything. So, what kind of university education to take? So, I took the most general STEM education I could find at Stockholm University, which started out by doing a bit of physics, mostly math, and a fair bit of computing. And then gradually you could specialize. And I quickly realized that the physics courses were not that fun. It would take too long to get to something interesting. So I kept to math and the computers. And then gradually I realized I'm too sloppy to be a good mathematician. But computers, because of compilation errors and obvious errors in the output, they force me to fix my mistakes. So that led me into computing. But I realized you can combine that with everything. So mathematical modeling became a thing I was interested in. I did a bit of virtual reality and I got into neural networks and computational neuroscience. And then, as I finished up my Master of Science, I decided, okay, I'm going for a PhD, of course, but I was also taking extra courses to actually learn neuroscience. So I went to the Karolinska Institute here in Stockholm. They had a good, solid neuroscience course. I took some courses in psychology, which was interesting, especially since a lot of what I learned in the basic courses is no longer true. Those psychology results have not replicated. A lot of the cool things that we're told about very seriously, they're actually a bit shakier than it sounded back in the 1990s, which is also an interesting lesson that you shouldn't trust what you learned back in your undergraduate era. You check that it's still true. And eventually, I got my PhD in modeling human memory. So I did this abstract neural networks, the models of general memory systems of various kinds. But that wasn't a good excuse for, of course, interacting with the AI and neural networks and high performance computing worlds.
Fascinating. So it's a lot of the same sort of problem that I think a lot of people face, where you're interested in too many disparate things, and you sort of need to focus in on something that's sort of most optimal to in the future go after those other things. I think that's something a lot of young people, myself included, struggle with, is so interested in sort of physics, computation, neuroscience, and then you're trying to figure out, okay, what blends all of these things together that I can pursue
Yeah.
and actually cause real impact. That's awesome. That's awesome.
Yeah. Yeah, and I think it's a really interesting problem how you manage your time. If I had been able to focus on one thing, I would have made a very efficient career. But I'm rather happy I didn't focus. I am happy I got this very broad education. That might have slowed things down. I was helped a lot by the fact that I'm in Sweden, so there is no real tuition, and you can even get some government funding for studying. I used up all the available government funding. Eventually, I reached the limit where the government says, "Nope, you should be finished by now." So that's where I had to kind of stop. But the cool part is, of course, you never know where your interest will show up and be useful. So I took a course just for larks, actually, about natural disasters. I literally took it because my then boyfriend and me, he was studying law at the university and I was in computer science. And we decided we should at least take one course together. So we took an introductory course to the natural disasters, which was very enjoyable, very fun, and very introductory. Most of the students were actually retirees who wanted to do something with their Tuesday and Thursday evenings. Later on, when I ended up in Oxford researching global catastrophic risk, having a solid grounding in natural disaster studies turned out to be golden. It was one of the most useful courses I ever taken, and I just took it on a lark.
It just shows sort of the power of following your curiosity at times. So you touched on this a little bit and its importance in your sort of following work in the future, but what else in university sort of were kernels of true inspiration in terms of what you continue to do in the future? You mentioned this class, but is there anything else that that you sort of remember from back then that definitely played a big part in what you continue to do in the future?
So a lot of it was recognizing that at a university you're in a system or in a big bureaucracy, and the bureaucracy don't care really much about you. People do, but the bureaucracy mostly care about you as a number. Ideally, students should come in, study, get a good result, and then the institution is getting funding proportional to that. So the institutions just want to shunt you around, and you see a lot of curricula and rules about who can take what courses and what the prerequisites are. And if you just believe those rules, it looks like a very hard game to play. However, you can actually talk to professors. You can actually show up at lectures without taking the course and just listen in. Um, Once you realize that there are people in these institutions, sometimes fighting against them, sometimes just going with the flow, but they're actual people, that is really valuable. You also realize that there are fellow students, some of which are really interesting. There is a lot of people I took courses with that just disappeared into academia and were doing these straight arrow careers. I got some people in medical school telling me about what you need to focus on in order to do a PhD on a hot topic. So then you can do your postdoc at a very important research group somewhere abroad. And then you can come back and later take over your professor's research group. And these people, I never really notice them anymore because they seem to have done good academic careers. They're probably professors by now, and they don't do any research I care about. All the people that do research I care about, quite a lot of them are weird people. They focus on things that are new, that are not fashionable, that later on turn out to be important. So several times during my university years, I heard about the interest in research, but many others said that's kind of weird and irrelevant. I mean, quantum computing, that's a weird peculiarity. We don't have such computers. Why should anybody bother proving theorems about what you in theory you could prove and do using that kind of computer? Well, it turned out to be a thing. That one, quite quickly, people realized that, oh, you can crack codes. That was probably a big deal. We should probably be doing more of it. Similarly, I was in neural networks, and in the 1990s, neural networks were kind of going into a slump. The reason was in the 1980s, there had been this revolution. Well, neural networks have this long story of booms and busts. So the perceptrons that showed up in the 50s and 60s looked like, oh, this is going to solve a lot of problems, and they're even inspired by the brain. This is super cool. And then Marvin Minsky proved that actually they couldn't do a lot of very elementary things. His book Perceptrons is really good, and it's an entire book-length explanation of why this doesn't work. He even explains what it takes to make it work. You need several layers. You need some way of correcting these internal layers, and he couldn't see a good algorithm for it. And then in the early 1980s, Hopfield and others came up with algorithm that worked. And they actually came up with a lot of really useful methods. And suddenly backpropagation was a thing. Hinton and others did it. There was a blossoming renaissance where people are applying it to brains. And this was fun for about 10 years. But then progress stalled. Those deep neural networks did really cool things for a while, and then nothing. So people started leaving the field. We, at my old research group, were mostly interested in the brain rather than a practical engineering application. And we're not so much into artificial intelligence. So we were fine with that. But many of the people who just want to solve problems of the computers, they were started this neural networks. And then there was this revolution of statistical machine learning. Basically, in the 90s, it was this realization, oh, this is what's going on. All these very different tools for learning things in computers are all special cases of a very general theory. Neural networks and the logic trees and a lot of other things, oh, they're all tools in the same toolbox. So a lot of people were even more abandoning neural networks, except for a few crazy diehards who then back in 2010s kind of got their revenge by suddenly taking over the entire field because now it suddenly worked. But a lot of the reasons neural networks worked in this century were totally unknown in the 90s. I remember telling my students about overtraining and lots of rules of thumb that made sense back then, but are no longer true. Again, just like the psychology course, some things do get overturned. And sometimes it's rather important things that get overturned. So
Yeah.
that we can be totally wrong about these things, I think that is super valuable to recognize. Another career thing is you want to have a direction. I always want to get to the future. I wanted the most futuristic things, not necessarily the most fashionable or useful stuff, but virtual reality seemed very cool. So I did a fair bit of that. Computer graphics is also very fun. I wanted to do brain-computer interfaces, so I took some course in medical engineering and realized how horrifyingly hard that was to do. So I kind of dropped that for the time being. I'm very happy that Neuralink and other more competent people are doing it now. Basically, if you're interested in a lot of things, try to make sure that you at least have a rough direction of where you're interested in. If you're interested in everything under the sun, you will just go around in a random walk. But if you're interested in stuff in one direction, you can at least do a random walk biased in that direction. You're still going to pick up interesting stuff on the way. You never know when taking a course in art history comes in handy, but you will tend to drift in the good direction.
Yeah, I think that's extremely important. I think one of the primary reasons is it's always the case that people sort of discount the edge cases, and people working at, the bleeding edge of any research field is always, in some sense, it's a group of people who seem very weird on the outset, especially in the present, and in the future they look very different, right? And so I think it's important to sort of keep that in mind. Your career speaks to a lot of that. Neural networks weren't seen to be as going to be as successful as they became in the 90s. And I think was it ImageNet in 2012
Mm. Yeah, so
that
ImageNet was kind of a breakthrough.
yeah,
And it's an interesting story because basically what happened was there was enough data to train on and enough compute to train on a very large network. I
yeah,
remember asking my advisor back in 97 or so, so what about deep neural networks? And he kind of told me, well, they did some cool stuff back in the 1980s, but it turned out to be a dead end. And that was true in 97, 98 because there was not enough training data around. It was tricky to get good training data, and scaling things up was tricky. When we were thinking about very large simulation, we're always thinking about getting the big supercomputer to run it. One of my students was interested in could you use these FPGAs, these programmable microchips, and he spent some effort on that, and it looked like it could be done, and there was some really cool stuff. But he was also mentioning that those GPUs might also be useful. If we had pursued that more ardently, we might have been at the cutting edge there. We didn't. That's another important lesson. You often have great ideas that you don't do and somebody else implements. And that's fine. Just make sure you keep on having ideas and implement some of them. Eventually, one or two might actually work out well.
right. It's mainly about ensuring you're a generative model instead of a static one. So
Yeah, always going for what others say is good is risky because, yeah, people know a lot of things. They have good taste sometimes, but usually the really cool things is the stuff that you may go from 0 to 1 with, that you take from absolute just nothing to, oh, this is a prototype. It's almost working.
right, right, very interesting. So just to get back a little bit to your postdoctoral research, I think you did in Bayesian attractor neural networks,
Mm.
if that's correct.
Yeah.
And I'm wondering
So,
how
so
that
this was,
sort of
oh, sorry.
yeah, I was just wondering how that sort of helped in your understanding of cognitive enhancement and your later work on that. How did your PhD work sort of fall into that?
So in the 90s, I was also starting up the Swedish Transhumanist Association. I've always been interested in questions about human enhancement. Again, it's all over the place, of course, if you read science fiction. Cyberpunk was going strong there in the 80s. So, of course, cybernetic implants and cognitive enhancer drugs were really cool things to think about. And while I was working on the neuroscience courses and medical engineering, I was, of course, also thinking about human enhancement. Indeed, that was very much a reason I took these courses. I wanted to see what could be done. And on one hand, it was very nice to sit in the medical school's library and actually read actual academic papers about cognitive enhancement drugs. On the other hand, a lot of them were also not having great big effects, and oh, it was hard to make neural implants. But I was engaged in setting up a community in Sweden talking about this. I got mightily distracted when the web arrived. So in the early 90s, some of my classmates had discovered its multi-user online text adventure games, the MUDs. And I kind of knew myself well enough at the point to realize I shouldn't even look at that. It's going to distract me too much. And very smugly, I noted that some of my classmates were indeed super distracted and disappeared into a world of computer games. Then the World Wide Web arrived, and I didn't realize how addictive that could be. So I set up a web page about transhumanism, which turned out to be kind of a second one in the world and became a big nexus. And suddenly I got a lot of people contacting me, and we started forming organizations. I became part of the Extropians mailing list online. So I started interacting internationally with transhumanists. So it was very natural for me to both try to organize transhumanism, talk about its ethical impact and the possibilities, which was also very good, of course, just for public speaking and engaging with other people and getting that self-confidence that, oh, I can represent a weird view, quite often a controversial weird view. So I actually need to learn how to debate this, and that's really useful. So while I was getting into the more computational part of neuroscience, it was very natural for me to try to see, can I enhance the memory performance of my neural networks? And not just by adding extra neurons to them, but maybe I can add some signals to it to increase how much it remembers certain memories, etc. And I could see interesting limitations and possibilities. So that was now feeding into my thinking about cognitive enhancement. And that later, of course, became my ticket to Oxford. Because I made a nice set of connections because being on the mailing list, I of course encountered another fellow Swede, Nick Bostrom, who was debating a lot of things and later on went to do a philosophy career where he ended up eventually at Oxford University, setting up an institute. And now he needed some people to work on cognitive enhancement with him. And well, I knew neuroscience and I was good at explaining it to everybody who cared to listen, which was very useful because the philosophers might know ethics well, but we didn't know about brains. Also, I could do web design, which was also super useful because back in 2006, nobody at the philosophy department knew how to do web design.
Right. I can imagine, not necessarily a primary skill set. Um, so
Not
yeah, how
really,
is it?
but it was kind of interesting because philosophers quite often have a lot of weird hobbies. So I'm a bit surprised that nobody else had that hobby at Oxford.
Oh yeah, oh true, true, true. I imagine, yeah. That's a very valid point. I'm wondering what sort of the core focus on of your 2006 paper was on cognitive enhancement, and sort of can you help us define what cognitive enhancement is?
Mm. So the idea is that our brains are an organ like the heart or kidney. They have certain functions. The kidney filtrates the blood, the brain regulates behavior, it does perception, it does thinking, feeling, etc. These functions, couldn't they be modified? Most obviously, of course, we can break them by taking various drugs or anesthesia or messing with the brain. But maybe there are ways of making them work better. So in the literature on nootropic drugs, there have been this idea that, well, there should be ways of improving memory. Indeed, it's kind of obvious that you can improve memory just by training yourself in memory arts. By learning how to memorize information, well, you can memorize enormous amount of information. So we already had a existence proof that goes back centuries that you can enhance brain function. Although in that case, mostly by learning a few mental tricks. Similarly, it's pretty obvious that you could enhance some forms of performance by taking a stimulant drug. But also, it was more and more clear that you can affect, of course, memory and learning. Various Alzheimer's drugs obviously try to ameliorate deficits, but in healthy people might work. So I would define a cognitive enhancer as something that improves one or more of the cognitive functions of the brain. Now, the tricky part here is that might not necessarily be a drug. It might not be an implant. It could be some form of training. It could be some meditation practice. In fact, does it matter whether it's something technological or non-technological? It turns out that a lot of people are much more ready to want non-technological enhancement. Nobody thinks that it's a bad thing that people train memory arts. But if people were to take a pill to remember more when studying, many people say that's ethically problematic, which is weird because when you start thinking about it, the amount of effort going into memory arts probably means that you need to have plenty of leisure time and spare time to do that, while actually a pill could be very cheap. It might actually be more equal in some sense than training memory arts. Similarly, people think some functions seem to be more sacrosanct than others. Some might be harder to change, like intelligence, because it's built on so many other sub-functions, while alertness is kind of easy in many ways. It's a relatively straightforward signal. You can take a stimulant to increase alertness. More interesting is also that there might be trade-offs. If you take some drugs, they focus your attention. You do one task, you focus on that, you ignore everything else. This is brilliant when you want to write your essay. It's maybe not so good if you're out in traffic. Might actually be quite dangerous. So there are these important questions. What does better even mean? Remembering everything you experience might sound great up until you have a bad experience. And indeed, you want to forget most pointless stuff. Most details of our days are not worth remembering. But you want to remember the important things or be able to pick up a small detail that you thought you had forgotten when it becomes relevant. So actually, you want your memory management to work well, but maybe not remember every single thing. So when you try to define what enhancement is, you get into both practical and philosophical problems that are really, really interesting. And then the real problem is, of course, we don't have great tools right now. Maybe we should develop them. But of course, right now, if you want to make a cognitive enhancement drug, uh, what are you curing? In order to make drugs right now in the current pharmaceutical regime, they have to cure something that is recognized as an illness. And just having normal intelligence and normal memory, that's not an illness. So the drugs that exist, they're kind of repurposed drugs for other conditions. Modafinil, for example, is a narcolepsy drug, but it also does improve a bit of executive function and alertness. So maybe we should change how we define medicine, which is, of course, a really interesting, primarily philosophical question, but also maybe a political battle. So now when I was at Oxford, I was, of course, engaged in all of these debates. So it's both an academic research into what is going on here, what can we say about it, but also a little bit of activism. Somebody standing up and saying, I actually do think we should regard enhancement as a valid medical goal. And it was interesting because this debate was very active in the noughties, partially because Francis Fukuyama had written Our Post-Human Future. So Fukuyama is a great public intellectual. Even when he's wrong, he's kind of doing useful things. So this book was a big broadside against the concept of enhancement. He was very much against it because deep down he's conservative and thinking an enhancement might be bad for our human nature. And then it's full of arguments, and most of his arguments are not terribly great. And since he was aligned with George W. Bush and his cadre of conservative bioethicists, a lot of the liberal-minded bioethicists immediately took the more transhumanist side. So you got this big, wide-ranging debate about it, which was very healthy also for us transhumanists, because we're kind of forced to come out of the cellar and actually argue in public and make sure we actually had valid, good arguments. That was really fun.
Yeah, I mean, I have to say, this is just so bloody interesting to me. I could go down 1,000 tangents there. I mean, I frankly don't even understand how everyone doesn't do this for a living. But so I'll start off with this. It's my understanding that memory size is sort of the amount of memory a human can contain is finite, right? It's about 2.5 petabytes. What's the, maybe you can give me more accurate numbers on that. I might be a little off.
Well, I don't think anybody knows an accurate number. I don't think we have ever seen a human get out of memory error. That doesn't happen. If I take a little neural network and I try to train it to remember more and more, eventually I reach a point where you get catastrophic forgetting, it all breaks down. But that doesn't look at all like what you see in actual brains. It's not like the elderly professor one day suddenly stops and goes nuts. Well, elderly professors do go nuts, but not because we know too much. They go nuts for completely other different reasons. So the interesting part is how much can you actually store in a neural network? And one way of arguing is that you basically get a few bits per synaptic connection. So we can say, okay, we got around 10 to the 11 neurons in all of the brain, and each of them have around 8,000 synapses. This varies a lot, of course, between different neurons. But now you end up with, okay, so now we get 10 to the 15 bits, give or take. So we're in the petabyte or petabit range. Now, the problem is that's not really how we remember things. When I encounter the concept of apple, I see something green, I smell something, somebody says apple, and various neurons in my brain get connected into a cell assembly or something like that. And next time I see that green thing and that smell, I might remember it's called an apple. That dynamics is making use of it in an associative sense. And then I see a lot of different apples. So it's not like I remember every single apple. They become some kind of representation, distributed across a neural network. And it might very well be that many of these representatives overlap more or less. They create associations, and they're probably also interfering with each other. Sometimes when you learn a new language, you have problems that some words sound so much like other words in your language that it's hard to disambiguate them. It's very tricky to remember that the meaning is very different. This is sometimes causing very amusing problems. Like in Swedish, roligt means something is fun, but in Norwegian, it means that it's calm. And I have a very hard time when speaking with Norwegians to use the word in the Norwegian sense rather than the Swedish one, which we both recognize and laugh at. The problem is when you build a big neural network, we're representing information in a much more sparse form. We're compressing information much more. It's not like we're storing little bitmaps and pictures of what was going on, but rather abstractions. And that is also why painters and artists need to learn how to draw things as they see them rather than what they know it is there. If you see an apple on a table, quite often, most of us will try to draw an apple out of memory or understanding that is an apple, rather than the colors and textures you actually see on the table. So a lot of early art training consists of take a photograph and put it upside down and now make a copy of that picture. So you learn the textures and shading instead of actually looking at what it is. But this is still a bit unclear. We have a good theory for memory for neuroscience, but it's still not a complete one. We still haven't gotten that real measure of how much of our brains we're using for memory. In some sense, I think all of our brains are doing memory, but different kinds of memories too.
Right. I mean, I imagine so fascinating. I imagine that it's sort of constrained still by I mean, same way that a neural network would be constrained by compute. I imagine there's sort of a finite compute to the human brain.
Oh yeah.
Um,
So one thing is nerve impulses move about the speed of sound, uh, which is fast compared to how quickly we move our bodies, but not terribly fast compared to electronics. And the reason they do it like that is basically that a nerve impulse along an axon in a neuron is almost like a domino pieces tipping over each other. Ion channels open, let ions flow through, that changes the voltage potential, that makes ion channels open. And that is fairly slow. So you can speed it up by adding myelin insulation around the neurons. That's what happens to speed things up about a factor of 10. But this is still pretty slow compared to electronics. So a neuron can't fire arbitrarily fast. A typical neuron doesn't fire more than maybe 40 times per second. There are a few really rapid firing ones, chattering neurons, that can do it to a few hundred times per second, but they're pretty rare. Most neurons don't fire at all most of the time. They're just occasionally sending off a little voltage spike. So when you start thinking about processing power here, a single neuron might get 8,000 inputs, and maybe it gets it at maximal rate, something like 40 voltage spikes coming in per second, and then it interacts on that. But that's still a finite amount of processing. It's pretty clear that our brains are bounded. We have a finite amount of memory. It might be big, we might be able to represent things in a very abstract and effective way, but it's finite. We have a finite speed, we have a finite processing ability. We can't keep concepts apart from each other. There is this famous paper, 7 plus minus 2, talking about how many things we can keep in working memory. And most of the time, we can't keep 7 things in working memory. That's usually a best case performance. Quite often, we should be happy we have 4 or 5 things in working memory. And when you overload working memory, it just falls apart and we lose track of it. Simply because our frontal lobes, where this seems to be happening, are not built for that. And of course, I immediately start thinking, can we add some extra computers to expand our working memory? What could I think if I could keep 70 things in mind at the same time? What could I do if I could send nerve signals at the speed of light? The obvious problem is I can't move my muscles that fast. They're also limited by biology, so I need an artificial body that can do it like that. So the transhumanist concept of expanding the human range links very much to these limits, which are big limits, but they're still quite powerful limits. In particular, our intelligence is pretty limited. The more you study, the more you realize how hard it is to actually think really well. Because you see a lot of other clever people do lines of reasoning that you think, oh, I wish I could have come up with that. Oh, that's so elegant. It's so obviously true. And I couldn't have figured it out in a million years.
Yeah, that's that's very true. Um, I mean, there's so much. So you participated quite a bit in the 2008 brain emulation roadmap, and I'm sort of wondering what the sort of the technical challenges you identified for full scale brain emulation were.
So the big three we were thinking about was, do we get enough compute to actually run a brain? Can we get enough storage and all of that? The second one was, can we scan a brain to actually get all the relevant data out of that biology into that? And the third one is, can we interpret the scan in such a way that we can get something that runs? Now, the compute side is doing fine. Everybody loves to say that Moore's law is dead. Even Gordon Moore, in his original paper in the 60s, where he identified the law, said that this can't go on forever. It's going to probably end in a few years. It's just that when you calculate computations per second per dollar, everything is still nicely exponential. It's just that getting serial computations done very fast, that had turned out to be hard. Microprocessors stopped getting faster around 2006 simply because you can't up the frequency, they tend to overheat, and it's getting more and more expensive to make smaller and smaller transistors. But that was not a problem because we started adding cores to the microprocessors, and then the GPUs took over, and now we have massive number of parallel compute. So everything is going pretty well there. And since everybody's now piling into cryptocurrency and AI, people are working really hard on the energy demands and all that. So no problem on that side. The scanning side was interesting. We were sitting there in St. Hilda's College in Oxford, envisioning wonderful futures where we might have an observatory for a scan of a single cortical mini column. So Ken Hayworth was sketching out what was needed, and we were skeptical that we could get enough computer memory to just store a scan. We might actually have to have this kind of physical tape system when neuroscientists were logging on to follow neurons, etc. We had a workshop earlier this year, and I was sitting next to a guy from Google, and he did a scan of a cubic millimeter of human cortex last year. This is 16 times bigger than that dream thing we had back in 2008. And it's an amazing data set because it contains everything, well, including a lot of weird stuff. Nobody has any clue what it is. So there is plenty of data here for neuroscientists to just explore, trying to figure out, why are these connections doing what they're doing? Is it normal for that little axon to twine around that dendrite like it does? Maybe this is common and we never observed it because normally we'd look in slices of brain, and now we can get it in 3D. We also got enormously cool new technologies like expansion microscopy, which we couldn't have imagined back in 2008. So expansion microscopy consists of that you embed the tissue in a kind of gel, and then you expand the gel so you make everything larger. So now you can see it more easily in a microscope. The big problem is that you can't go to an arbitrarily low size scale with optical microscope because light waves are too big. They're several hundred nanometers big. So you might use an electron microscope, which has finer resolution, but also fries the tissue quite badly. It's harder to get chemical information out of an electron microscope. Or you expand the tissue, so you can use optical microscopy to see details that previously would have required an electron microscope. And there's a lot of clever stuff going on in the world of microscopy these days. Biotechnologists like Ed Boyden are doing amazing things with modifying neurons to express colors and proteins that give you data about what we're up to. We're thinking about molecular ticker tapes that document the firing pattern. There are other ideas about having synapses get each individual little numbering code so you can figure out the connectivity on a molecular level. So we're getting a lot of really cool scanning technologies. The part that has not developed as much as I wished, because it's a tricky one, is if I have a scan, can I now turn this into a simulation? So back in 2008, we were kind of mildly hand waving that maybe, just maybe, you can just look at these electron microscope scans and turn that into something you can run. And I think nobody really believed in it. I have been kind of waving about it half-heartedly and hoped for it, but it's pretty obvious that no, we need to get the chemical properties, we need to get the electrical properties. That's going to be really tricky to measure. And indeed, in the meantime, the most promising organism to study this in, the little nematode worm C. elegans with 303 neurons, turned out to be really hard to simulate. We had the connectivity, but not the parameters. And that failure has been kind of a big embarrassment. There is a good reason why it's been a failure. It's simply too small to do easy experiments on. So what has happened is that people started scanning larger organisms, like a fruit fly. And indeed, now we have a fruit fly connectome, which is gorgeous. And it turns out that you can infer some of the connectivity data and the chemical data just from these scans. Not perfectly, mind you, but well enough that you can actually run simple simulations that actually produce some typical fly behavior. That is astonishing to me. That weird dream that I used to be hand-waving about a bit half-heartedly turned out to be somewhat true, at least. That is really good news. It's still, however, up to us computational neuroscientists to bridge this, and we probably need to develop a very different research program how to do translations of scans into models. So there is plenty of work that remains, but it's astonishing when you start a field to see just 20 years later that, whoa, things are actually starting to move, and they're moving fast.
It's fascinating. I've seen, I think, the connectome for C. elegans. I'm not sure if we fully, I might be talking of a separate animal, but I mean, what's fascinating about that is it the scale up that yielded better results to to an animal with with more connections, or what is it that yielded better results?
I think it was that if you have a bigger brain with more neurons, it's also more forgiving. If you get the interactions between two neurons wrong in C. elegans, well, that's 2 out of 303 neurons. So probably the whole network is now behaving wrong. I can imagine that a fruit fly, they probably have a few special neurons that do a lot of work, but there's probably a few doubles and copies. So if stuff doesn't work quite as well as it should, you might still be able to get a lot out of it. It could also be that these experiments didn't work for many behavior, but just a few very strong behaviors. So I think we shouldn't be making too much hay about it yet. But it shows that bigger might be more forgiving. And that's, of course, what we found with the neural networks in our AI applications too. Turns out that having a very big neural network that you train with a lot of data is way better than a tighter network. I believed honestly in the 90s that, of course, you should have more data than you have connections in the network. Having a big network, oh, that means that you get overtraining. It's just going to be parroting the information you feed it. And that was kind of true for the small networks, but now we have over-parameterized networks that actually work really well. But they need to be much bigger, and that was not obvious at all before you tried it. So another important lesson is sometimes try to do the stupid thing at scale. It might just work. And usually you will have a professor telling you very sternly beforehand that this is a stupid thing to do. Hopefully afterwards they will tell you that was a stupid thing to do. Congratulations to your Nobel Prize.
Yeah, yeah, that's always an interesting one. I think one of the things that's been most interesting to me that sort of aligns with this is seeing how you can get these, incredible improvements in output text generation, these large generative models, when you scale them up relative to making no changes algorithmically. So I think that speaks a lot to just sort of some of the impact of just scaling up compute resources.
Mm.
So that doesn't obviously map one to one to the human brain or any other mind. That's
Yeah,
very
that
interesting.
is an interesting part, actually. What happens if you double the human brain? I don't think anybody would expect the result to be, oh yes, now you get twice as smart or something like that. Now, that doesn't seem to follow. But there is something about scaling things up and certain things and understanding those scaling laws have tremendous power. And this goes in a lot of other fields. One big influence on me has been Eric Drexler. He's the father of nanotechnology, and he's also a very, very good engineer. So I've been kind of learning from him to do these scaling arguments, because if you look at nanosystems, a lot of his arguments for why nanotechnology work is just pointing out that if you scale down the size of a machine, certain things scale up, some things scale down. And if you look at the scaling laws, you can actually talk about the performance and see why this has a lot of interesting effects. So when you make things smaller, of course, it moves faster, which is, of course, also why microelectronics or nanoelectronics gets better and better the smaller it is. Eventually, nanoelectronics runs into the molecular level, and that happens to nanotechnology too. But those scale ups or scale downs are really important for seeing why you really want to do it, why things move faster, why you can get more throughput. And it's a very easy way of reasoning once you get used to it. It's a bit like Fermi estimation. When instead of calculating laboriously everything exactly, you make an order of magnitude estimate. Being good at that is a superpower. And it's a really nice way of orienting yourself towards problems that have a big impact. And it's just that we don't understand the scaling laws for brains very well.
Right. I think with many other things we don't understand. Yeah, that's very true. One of the people that I find super interesting in this sort of arena, and if you take your idea of needing to understand sort of the chemical interactions to its limit, is someone like Donald Hoffman, who speaks about sort of needing to map out the Markovian dynamics of, pre-space-time objects and then mapping that down to consciousness, which I guess has some interplay with the brain and might help us understand, you know, what mapping some of the more fundamental sort of smaller structures and then all the way up to sort of neurons might do in sort of building brain emulations. I'm not sure if that's. I mean, we're quite a ways away from that and doing anything sort of technologically useful, but it's an interesting idea to play with.
Yeah, and I think there is a valuable core idea too. So one of the things I learned throughout my career is kind of treasure those really good ideas that can be used somewhere else. So Jürgen Schmidhuber early on had this idea that maybe a lot of intelligence is compression. And then, of course, he's totally over applying this to everything, which is fun. But when you have a good idea, try to throw it at everything around you, see where it sticks. You just need to remember that just because it could perhaps just stick doesn't mean it's actually working. Be critical about it. But that thing about compression as being part of intelligence is really valuable. It fits in very nicely with David Deutsch's idea that what makes us special is that we're good at making good explanation. And a good explanation is a kind of compressed representation of something in the world. It's not just that it allows us to say, now I understand why that happened, but you can make predictions. You can kind of run your explanation in your head and see what happens if I do this and that. And the really good explanations are very generative. And now you can go off and do things because you understand or think you understand something. Now, the cool part is also when you say compression, the kind of theoretical complexity people peek out from their offices and point out, yeah, and that is a really computationally hard problem. Making a compressed representation of something is in general empty hard and you can't do it. And then they disappear into their offices feeling smug that nobody has ever been able to compress anything, which of course we know is totally untrue because we're doing compression all the time. Our computers are doing it really well. It's just that it's not perfectly optimal. And yes, there are special cases that don't work. And when we look at the world, what is easy to compress into explanations and hard to compress into explanations, knowing the difference between that is really valuable. And again, you can orient yourself by seeing, oh, that's a tough domain. That doesn't look compressible. Maybe I should stay away from it or work along the border. Again, the edge of chaos is another one of those nice concepts. A lot of interesting things happen when you get from the borderland of very predictable to very chaotic. Usually nothing interesting happens on the chaotic and the predictable side, but that borderland, that's where you get interesting complexity, and the value of the hard work of finding explanations there is often quite high. So then you end up with these little half-baked heuristics going through life, and if you're lucky, you can then apply them and get good stuff going.
Right. Right. I think we could go on and on about sort of some of the more detailed aspects of this, but I think it'd be interesting to touch on because you worked on a lot of the moral aspects of cognitive enhancement as well. And you wrote a paper on this in 2009. I'm wondering what some of the core moral dilemmas are, core moral issues might be.
Yeah. So I think generally being kind of in favor of cognitive enhancement, I think generally what we're not to like. And you can obviously say, yeah, but some things are risky and dangerous. Yep. But that's not even a moral thing. That's just we need to manage the risks in the right way. And it might be that we need informed consent. Maybe people shouldn't be taking stuff willy-nilly. You might want to have a doctor oversee things, etc. There is another part, and that is about justice. Well, if some enhance and some people don't enhance, isn't that bad? And that goes, of course, with any other technology. So enhancement might not be particularly special here. We might say we want to set up systems so they're just enough. So it might be wrong, for example, in sport, if some use doping and others don't. That's not a fair comparison. On the other hand, if I want to learn something and take an enhancement, I might not be competing with you. If we're trying to compete for grades, maybe there is a problem. So we need to understand the kind of game we're engaged in and whether enhancement is a good part of that game or not. And we might conclude that, yeah, maybe in the Olympics, it's not part of what we think the Olympics should be. But if we want to kind of prove mathematical truths, well, take whatever enhancement you can find because we want to get at the truth. I think many of the issues that are really deep has to do with the control of our own bodies. So I've been a proponent of what I call morphological freedom. Your right to your own body extends to your right to modify your body or not to modify it. So if my boss shows up and says, Anders, you should be totally taking the stimulants not to sleep so much and produce a lot of nice papers, maybe I'm happy with that. Maybe not, but I should be able to say no to him about that because it's about my body. He might be able to tell me what computer to use in the office, and I might have equally strong opinions about that. But that is kind of outside me. I don't have a same kind of moral claim to what kind of laptop to use. Now, the interesting part here is, of course, how to negotiate this in a useful way. I originally argued in my paper that this is mostly a negative right. Others can't force me, but they don't have to support me. There is a bunch of disability rights activists thinking that I'm too conservative here and it should be a positive right. We should actually have society support this. They are, of course, mostly thinking about being differently embodied. They think that there should be ramps for people in wheelchairs. The wheelchair people are not handicapped. They're just differently embodied, and we should have a society that works for everybody. And you could make the same argument that enhancement, maybe society should be paying for that. And depending on what kind of healthcare system and how competitive society is, you might end up in different views there. This shades over into politics and it can get rather interesting and rather intense. I'm kind of leaning towards a wussy libertarian side. I'm a Swedish libertarian, but I have friends like James Hughes, who is an American social democrat, which means by Swedish standard he's a crazy libertarian, and of course by American standard he's probably one of those dastardly red socialists. It's very interesting when you move around international to realize that political views are quite variable and quite often local to their societies. The question might be the same, but how people express it gets very different. In Germany, because of their past, they're very, very concerned about enhancement and generally, ooh, that's scary and creepy. But also privacy is super important. So anything that invades privacy is even more red alert. While in the UK, people are free to do whatever, but everybody assumes the healthcare system is at the breaking point. So whatever you do, don't touch the healthcare system,
Yeah.
and so on. So the deep ethical questions that Fukuyama and others say we should not play God or human nature, I don't think they're that powerful. They're great for having a philosophy seminar, but we're not going to determine what we do in society. I think it's more the practical stuff. Can we get something that is cheap, safe, and effective? Can we get it approved? Can we have a control system that gives you quality? Can you have consumer reports for enhancement? Might there be better ways of getting the same result? Sometimes, after all, you don't want to do biomedical enhancement if you can do a social change. And some social changes might be very hard to do and it might be easy with biomedicine.
Yeah. I mean, one of the things about this, and I think this is such an important topic for so many reasons, is, is sort of how profoundly this changes the game theory of current society. Um, I think it affects everyone across every scale, across any sort of denomination you might have. Um, and I'm sort of curious how, and you touched on this a little bit as to like, you know, certain people are more enhanced than others. And it might be interesting to know that I think in Austin, I think just recently they had the launch of what's called the enhanced games, which is I think an entire different competitive league for people who could, you know, are fully allowed to enhance themselves in any way they see fit. So I think that's an awesome push in that direction. But I'm just wondering how much of the game theory of modern life would have to change and sort of some of the ways in which people who have deeply held theological beliefs um, might be, you know, unrooted.
Mm. I think a lot of people are getting unrooted for a lot of different reasons. So another of my general recommendations is, of course, read widely and read old books. It's really interesting to read the books from previous generations that were influential and realize how much stuff has changed. So if you read the stuff from the early part of the 20th century, a lot of people there are living in anguish because we're not as religious as the parents were. And yeah, I don't think we see that very much. We kind of got used to not being terribly big believers. Even in America, non-belief is fairly normal. Yeah, there are some places where it's less normal, but we kind of gotten over the death of God to an enormous degree. That would have seemed crazy if we go back 100 years. And I think many people are having this unrootedness for various reasons. And indeed, there have been these wrenching transitions. We have moved from the agrarian society into the big city. That changed the nature of the family, the nature of social contract. We have a big ideological struggles about what shape of society there should be. Society got global. Suddenly we need to deal with people from different cultures, not just immigrating near to us, but also working with us, sometimes physically, sometimes owning the company. And we need to start figuring out how to handle that kind of global world. And then you have this challenge to our biology. It's not entirely new. The contraceptive revolution in many ways was an equally big unrooting. Suddenly, sex and fertility became separated. That was an enormous upheaval. It was before our time, but when you talk to older people, it's interesting to hear how that really changed things, because two things that were always linked to each other suddenly didn't have to go together. Suddenly, sex could be just for fun, and that got a lot of people very, very upset. And it is a profound change. So I think in many ways we are going to see a lot of people very upset and unrooted by enhancement. But I also think we kind of get over it. But it might, of course, introduce other tensions. Right now in the US politics, the culture wars is in many ways the unresolved tensions that have been left for a lot of these previous stages. They don't go away, they just take new forms. And in many ways, we might not care about some aspects, but there is still tension there. And it's important to figure out how to deal with it. I think yes. Yeah. So I think one interesting aspect is, of course, societies have a lot of different focuses. Many societies tell themselves that we're all about one big thing, and that usually doesn't hold water very much. So the American dream, yeah, it's an important concept of the mythology of America, but there's a lot of stuff going on. People are making families, people are competing, people are cooperating, people are exploring and doing all kinds of stuff. And okay, now I think we got a break again here.
Yes, sorry.
Yeah.
Keep going. Sorry about that.
Okay, yep. So I think societies are about many things at the same time, even though they might put this big label, the American dream, the people's home in the welfare state or whatever. But what then happens is, of course, that different cultures also have different emphasis. American culture, for example, is pretty competitive. So the first thought everybody has when talking about enhancement is, how is this going to change competitive pressures? And indeed, in less competitive cultures like Europe, people are worried that what if we become like the Americans? We're using the enhancement to get ahead, and we're becoming super competitive, and we don't want to be that. So there is a lot of this discourse about how it fits into a culture. On the other hand, enhancement is quite often framed in a workist mode. We're talking about enhancing mental capacity and skills. It's very much not recreational, because recreational drugs is seen as a separate mental category. And it's not therapy. We're seeing that as separate. And the way enhancement kind of allows itself to getting into a serious debate is by saying this is for work. Then it fits with the Protestant work ethic, and it becomes hard to argue against it. But I think many of the enhancements we probably truly should want is things that make us more deeply happy, something that makes us sleep better, have nicer daydreams or whatever. But that's much harder sell. So saying something that makes you work better economically is good. But of course, in reality, what the systems get used for once they're out in use is very hard to predict. The computer was intended to simplify mathematical calculations. It turns out to be a universal tool for information processing. And before long, it's being used for pornography and cat videos and stock market operations. And people are making silly websites and world-changing ways of doing science. It's used for a lot of different things, many of which were definitely not intended. And I bet that successful use of enhancement is going to be all over the place. There are going to be some uses we can't possibly imagine, some which we might say are utterly frivolous and bad, and others that kind of, oh, what it was sad that we didn't realize ahead of time that these possibilities existed, because then we would have pursued enhancement with great zeal decades before. But we can't predict them before they happen.
I think you touched on an incredibly important point in saying in a large part, I think the mythos of a culture really plays a part in how willing people are to adopt some of these ideas and sort of accelerate them. So that's fascinating. You know, one of the things that I think is just like super interesting about what you've done is you've gone and you've seen all these disparate fields and you sort of tried to aggregate your knowledge across those disparate domains. Um, and one of those domains is existential risk. And you work primarily on sort of low probability risks. And I'm wondering, what are the tool sets that, because most people don't even come across things like that in real life, or people like you who might have worked on stuff like that. So what are the tool sets? Why is it important to focus on existential future risks um, that could be, completely improbable at times, sometimes more likely than one would think?
I think part of it is, of course, that my optimistic view of the future means that, okay, there is much to lose here. And if you're not a Pollyannish believer that everything is just in the best of all possible worlds and everything is going to turn out fine, once you start thinking about very powerful technologies that could transform the world and humanity radically, ooh, bad uses of these technologies could be really bad. It's not a coincidence that a lot of the people taking existential risk seriously in the late 90s, early 90s came from the transhumanist movement. Because if you think that the potential future upsides could be vast, then by symmetry, you should expect that there could be negative downsides that could be equally bad. So you might want to fix that. And of course, the optimism involved here that maybe we can fix it is also really important, because you never know actually if you can do something, but you need to have that self-confidence that, of course, we should be able to budge these probabilities. So one of the key mental tools is just be able to do mental scenarios. Could you get a situation where a particular technology gets misused? And one of my many hobbies is role-playing games, and it's great for improvising quick scenarios. And of course, as a game master, it's very fun to think about that device, that technology, that weird planet or alien species. How could that be misused or dangerous or create an interesting story? So it's easy to generate bad scenarios. Then you want to start thinking about the plausibility about them. And this is tricky because it's not just probability theory. Probability theory is an awesome superpower to have. And if you're really good at using Bayesian reasoning, you have a mental superpower that's really valuable. But you also need to be able to reason about things where we don't have proper probabilities, and you want to find other ways of handling it, like dominance. That one thing is clearly more likely than another thing. We don't know the likelihood of either of them, but we know that if the second thing is smaller than the first thing, and the first thing is not important, then I don't have to care about the second thing either. Or maybe I can see other mental tools to do approximate reasoning here. So you use tools like scenario planning, probability, plausibility reasoning, and then you might want to develop that to a skill. And quite often, this is used to loosely find where are the dangerous points? Where are points where it looks like there could be trouble? And then you want to inquire more strongly into that. The exact probability of a nuclear war is hard to estimate, but we know a fair bit about how the mechanics of nuclear war works. We know a fair bit about the diplomatic state of the world. We can interview people like Ellsberger, who were in the loop, and they can tell us things. We can learn useful stuff and then start thinking, can we fix the system? That is one of the most important part, I think, of existential risk research. We have spent a lot of time identifying possible risks. Figuring out roughly how dangerous they are is valuable, but if you just know that probability and cannot do anything about it, it's still pretty worthless. At most, it sets a discount rate for your future. You roughly know how long it is going to be before that risk gets realized. But if you can do something about it, you should, of course, put your whole heart into that. And that is, of course, where other skills come in handy. That's where you need your diplomacy, your technical skill, your sheer chutzpah, or just energy.
Absolutely. Can you touch a little bit on a concept you introduced called the anthropic shadow, and how
Mhm.
that concept sort of helps in this pursuit?
Yeah, so the anthropic shadow comes out of what's called anthropic reasoning, which in normal parlance is what we can say observer selection effects. So there is this funny situation that on average, your friends have more friends than you. And the reason is that it's a very skewed distribution of number of friends people have. A few people are super gregarious, and you're pretty likely to know one or two of these people because they're super gregarious. So on average, your friends have more friends than you, and that sounds very weird, but it's of course just because of you're a random person in the world, and most people are not super gregarious people. Similarly, if you go out and try to catch fish in a net, you're not going to catch fishes smaller than the size of that net. So if you believe that what you get in the jar after fishing is the fishes in the lake, you're going to be wrong. This gets really tricky when you start thinking about human existence and the survival of human species. We cannot evolve on a planet where life goes extinct before we show up. So clearly, our existence kind of presupposes that life has never gone extinct in the history of Earth, or at least not for the past few billion years. Maybe the life emerged and got whacked immediately, and then it emerged a few hundred million years later. But that was kind of in the hazy past, many billions of years ago. For the last 4 billion years, life has been an unbroken chain. And this, of course, means that you get this weird situation that certain big disasters might look less likely simply because we exist. You could imagine a universe where giant asteroids frequently hit planets. A few planets are super lucky and are never getting hit. And that's the only place where you get observers. All the other planets, they are getting hit constantly. They're just big lava fields. And the inhabitants of the very, very rare lucky planets, they're looking around and saying, the universe looks very safe. We haven't found any giant meteor impact in our entire past. Oh, what a wonderful world we're living in. Well, of course, next week they're going to get whacked by a giant asteroid because very likely. So what I argued in this paper was basically that we might have this shadow effect for big asteroid impact and supervolcanic eruptions. It's a small bias, but it's an interesting one, and you can try to apply it also for nuclear war. We have had more than 75 years with no nuclear war. This is great. That seems to imply that the world is pretty safe. Not so fast, the gloomy doomsayer will say. Maybe we are in one of the few worlds which is not a radioactive wasteland. Maybe only observers exist in a few ridiculously lucky worlds, and that means that our prospects look pretty glum. So I have an as yet unpublished paper where I try to correct for this. And the good news is there are other reasons to believe that nuclear war is not super likely, which is good news. It's still kind of worrisomely likely compared to many other risks, but the anthropic shadow doesn't bite in here. We can kind of determine that. So this kind of weird probability reasoning is very valuable when you don't have much data. When you have a lot of data, go with the data instead because it's much more reliable than any kind of reasoning I can do.
Right. One of the things that I've long wondered in terms of mapping out existential risks are the use of prediction markets. Now, I understand that consensus isn't always the best thing because you can have madness in consensus, but I'm just wondering if in any part of your work that's come up using sort of market structures to help better gauge um, sort of the input of information and then the analysis of it.
So I haven't used the information markets and prediction markets myself. I participated in a few, and I've been friends with Robin Hanson, who's kind of the big proponent since forever. So it's very fun to see how they have developed, and they sometimes do seem to be getting things very right. It's kind of interesting to see them applied to American politics, because American politics is a spectator sport very much. Um, but I haven't been using them myself, partially because many of the questions I'm most interested in are so far in the future that the markets are at most going to give you a kind of rough consensus, but people are not going to be serious about it. It's worth noticing that action markets are also, of course, prediction markets to some extent. They're putting in information from all directions and trying to judge things. So I've been working a little bit on the question whether you could even argue that supply chains act as a kind of neural network, that we literally have a form of distributed cognition happening in the market, which is not a too heretical view. Most economists who read their Hayek would say, yeah, that's roughly right. They might be debating how metaphorical to take it, but there is certainly a lot of distributed cognition going on. And I do think that we can refine these tools. I'm very curious to see how we can add large language models and other systems to get different points of opinion about the same question. Because one of the big insights I got over many years is that asking one expert for an opinion, that's nice, but you should ask several experts, and ideally a few non-experts, and ideally a few very different takes on it, because you want to build a picture that's much more many-sided than just what is the received wisdom from the greatest professor in the land.
Absolutely. Absolutely. And I think, especially in this sort of existential risk mapping area, one of the more useful things would be to have a sort of a bunch of experts calibrate their sort of accuracy over time, rank order all that stuff, and then have some way in which you can input and sort of use market structures to gauge. I mean, in some sense, you could use the market structures and still filter out for all the experts within a relevant field, right? You don't need to get the consensus from a bunch of people who don't have any pre-existing knowledge for a given area. But yeah, I think
Well,
that's
you
super.
want to bias things towards people who are good at predicting it, and that
Yeah,
might very well be the experts, or it might be other people. So
yeah,
one of the biggest results in recent years in forecasting is, of course, the super forecasting tournaments, and it's kind of amazing that this is a finding that is about a decade old. It's kind of insane. Why didn't we have that in the past? People have been trying to do forecasting for a long time, and it's mostly been treated not very seriously. Most forecasting is more entertainment than an actual attempt at saying something sensible about the future. And when EARPA started their forecasting tournaments, it was kind of astonishing to find that they actually found a workable method and methodologies that allow you to do it. And it works pretty well in some domains. Again, super forecasting teams don't forecast things very far into the future. They need to have enough information, but they're significantly better than just taking a typical intelligence analyst or some random expert or a random person on the street. That is valuable knowledge. It's also valuable to know where the realm of application stops. Some things are simply not predictable. Some things are just, okay, we need a theory of some other kind. Some things are just going to be, we need to be adaptive about it. And this is extra important when thinking about existential risk. It's not that important, perhaps, to know the probability of certain risk. It's rather important to see, is something happening right now that we need to react to? So you might want to, instead of trying to predict when the disaster happens, because that's very likely to be unpredictable, you want to be ready when it occurs. When you see the first small signs, you want to move in. That unfortunately didn't happen very well during COVID. It was kind of clear rather early on what was going to happen, but many authorities around the world were too slow about it. Even good plans that had been made beforehand about what if we get a pandemic of an upper respiratory tract disease got literally binned in the US government because of political expedience. That's kind of embarrassing. We might be having exactly the same situation about the current bird flu situation. We're almost perched on the spillover, most likely from cattle to humans. It might be possible to avert, but that would take political capital, and most people don't seem to be willing to do that in policy making in the US. So the smart money, I guess, is right now that, okay, we're going to get that pandemic happening. Let's hope it's a mild one. Now, the
Yeah,
problem here is, okay, you still need to do the politics here. You still need to figure out how do I set up this early warning system and have enough capital to move out with sirens blaring when it's time. Especially since if you're very successful, it's going to look like it was all for nothing because nothing happened. Many people have totally forgotten SARS-CoV-1, which was way deadlier than the COVID-2 pandemic, but it was actually stopped after fairly significant effort, but it was stopped. It was just a few thousand people involved. That was a success story, but people forget the success story, sadly. So maybe we need to raise more monuments to the successes so we don't forget it.
absolutely. Absolutely. It's one of the greatest issues of our time. So just to sort of touch back on your track, you focused quite a bit on sort of the ethics of space exploration, some of the pitfalls that human beings might face as we sort of endeavor into the final frontier, hopefully. I'm wondering what you think sort of some of those ethical dilemmas might be, some of the issues there. And I know that's a pretty big field, but what's
Yeah.
your focus on that bit?
So I think the near-term situation is that we're putting a lot of very expensive things into an environment that's very harsh, and when stuff breaks, it really breaks. It tends to blow up spectacular. It's enjoyable when it's kind of SpaceX and Elon says, "Oh, I totally intended to do that." It's less nice when people get hurt, and we are going to put more and more important infrastructure in orbit. You don't want a Kessler cascade where an orbital debris from broken up satellites hits other satellite and suddenly entire orbits become unusable. So you need better coordination mechanisms, and that's going to be tricky because we also have a little bit of a new Cold War. The US and China are not playing well along with each other, yet we need to probably have traffic rules. We need to set up ways of handling it. And the old the international treaties, they need to be renegotiated anyway. So there is an interesting opportunity here of trying to get space law, if not right, at least better. And because whatever is decided in the next decade or so is probably going to last for a few more decades and set a lot of important constraints on what later gets developed. But this is a practical prudential thing. It's not necessarily a profound ethical issue. One I've been working on is about the ethics of spreading life in space. So I'm generally a biophiliac. I really think that life has an intrinsic value. It's a good thing that living organisms exist, and I think there should be more life and complexity in the universe. Go life. I want to spread it around. And there are people saying we should totally do directed panspermia. We should send out space probes with the bacterial spores in the good containers and make sure they end up in the life zone of other stars. Because if this is the only planet with life in the universe, we have a duty to spread it. And I think this is a really good idea. However, I'm co-authoring a paper with a friend and colleague, Asher Sorrell, who's taking a very different tack. He points out that a lot of living organisms have lives that are not great. A lot of wild animals meet a totally grisly, horrifying end, and there is a lot of pain and suffering in the world. And by some ethical accounts, actually that pain and suffering has priority. The fact that we're beautiful butterflies and some happy people, that might count nothing compared to all the anguish of an organism starving to death or getting eaten by parasites, etc. So spreading life willy-nilly across the universe might make everything way worse. So Asher and me have a very fun back and forth in this paper. We kind of conclude that we are uncertain here about what the true moral stance is. If there is a real perspective of the universe, uh, is it on my side or Asher's side? We don't know yet. We need to do way more philosophical research about that. And that might mean that we should hold off on spreading life in the universe. That might actually be the most ethical thing we can do. I think that, yeah, waiting a few decades with starting new biospheres, that's not that bad. I mean, biospheres last for billions of years. What is 1 decade of a biosphere's history? You might be worried about existential risk. So you might imagine something like a dead man switch. But if everything is going to heck in a handbasket on Earth, we press the button and launch the bacteria spores and hope that they do a better job somewhere else. So you might find workable solutions for that. I think the deep ethical issue is that right now we're all on one planet. We're all in principle able to talk to each other. We might disagree, we might have very different views on what should happen to the world, but we are close enough that we can negotiate and discuss that. As soon as we start moving far into space, that's going to cease to be possible. Uh, in the solar system, maybe we can send each other an email, but once you move to other star systems, it's going to be years before the cease and desist letter arrives. And once we're spreading sufficiently far, the expansion of the universe makes it absolutely impossible to influence each other's behavior. That means that we might want to coordinate a lot of things before we spread too far. We have this golden opportunity right now to figure out some ground rules, some things that let's never ever do this, let's make sure we do some other things. This might still take a while to hash out, but that's fine. I think we have a few decades at least before we irreversibly spread across the universe. But I do think that is an important ethical consideration.
Absolutely. I think and it's one of the most exciting fields to work on. And I think one of the more practical things that I don't hear many people talk about that I found interesting for many years is what money will be used in space, right?
Aha.
It's often that you hear conversations that don't have much to do with economics with space, and it's a lot of this fantasizing and philosophizing. But like what is the money that we're going to use in space? It's a pretty critical question. I haven't seen
Yeah.
a good
Uh,
enough answer to. But I think, there are some answers that have emerged in sort of this parallel world of blockchain and cryptocurrency.
Yeah, but
Yeah,
blockchain and cryptocurrency has this other interesting aspect. Time becomes linked to it. So if you're a blockchain enthusiast, you have this problem that the Earth blockchain and the Martian blockchain, it's going to take a while for them to synchronize. And it gets even worse when you have a blockchain at Alpha Centauri. So Charles Stross in his novel Neptune's Brood is playing around with this. He actually spends quite some time thinking about the different kinds of money an interstellar civilization would have. And there is the slow money that is kind of negotiated between different star systems. It literally takes many years before a transaction goes through. And then, of course, for everyday use, you use the local fast money. But I think there is a more deep problem. That is, how do you even pay for going to space? So tying back to kind of my origin there, reading all the science fiction books and thinking about, oh, yes, we should totally go to space. Back then, I was never really thinking about money in regards to space. I was, of course, thinking about pocket money so I can go buy an ice cream. That was kind of an important investment for 6-year-old me. But when you want to build something in space, you need to pay for it. And ideally, you want it to pay for itself. So what do we have up in space that pays for itself well? Well, communication satellites and Earth monitoring satellites. Then we have a bit of science satellites, and they're kind of not paying for themselves, but the research projects are interesting, cool enough that humanity as a whole actually puts in money. Many people say humanity is very pragmatic and doesn't care about that kind of stuff, but it's worth noting how much we spent on astronomy throughout human history. And that's not all about astrology. We have this deep yearning to see the universe and know what we're part of it. So I think we're always going to spend some money on that. But it's rather hard to find that great business opportunity. So in the 1970s, Gerald O'Neill did these famous ideas about homesteading in space and space-based solar power. And he basically argued that, yeah, let's put industry in space, let's put energy production in space. That's going to pay for space. It didn't really happen. Partially, of course, because stupid things like the space shuttle and the people not going for this optimistic good vision, but also because space-based solar power is actually quite unwieldy. Elon Musk actually convinced me with a literal napkin calculation that it is going to always be beaten for Earth purposes by solar panels on Earth, because you can repair them in your shirt sleeves and you don't get the big transmission losses. And if you want to reduce transmission losses, suddenly you got a death ray in orbit that can wipe out the White House in seconds. Oh, that's a hard business case to sell. So generally, the constraints are tricky. It doesn't look like that kind of space industry automatically becomes a big thing. Certainly, Jeff Bezos thinks something like that, so he's aiming at that. But we still haven't gotten that great idea for making money in space. It might be that the only way of making money in space is selling stuff to other people living in space because we moved there for crazy reasons, or because they want to join Musk will to be a multiplanetary civilization. But that's not going to lead to a rapid settlement of space. It's going to be one of those extra weird things humanity can afford to. But the technologies we need to do it in space are, of course, tremendously useful down on Earth. Renewable energy sources, perfect recycling, automatic mining and manufacturing. That's super valuable. Enclosed ecosystems for agriculture. Perfect. If that works in space, you can plonk it down on a parking lot too, and now you have your urban garden and a safeguard against a lot of disaster. So many of these technologies are useful, but would be even more useful down on Earth where most people live. Even if Musk moves to Mars, he's going to be rather annoyed that he's not getting rapid updates on his stock market ticker because most of the economy for a long while is going to be around Earth. Eventually, I think we are going to get away from that, just like we migrated from the most pleasant part of Earth to crazy, weird parts of Earth like Scandinavia. Every winter, I'm kind of wondering whatever got into the heads of my ancestors moving here. This is a stupid place to live. But they did, and now we live here and we built an economy, and people are opinionated about not moving away even in winter. And I think the same thing eventually happens to space, but it might be much slower than we might want it to be.
Yeah. And I completely understand why your people moved to Scandinavia. It's a lovely place, but it's,
In
you
summer,
know, one of
yes.
in the summer, true. One of the things that I find it's interesting that you mentioned sort of energy production moving to space. One of the other really important things that space has that's sort of a critical resource is the difference in gravity. I think that's extremely useful in sort of 3D organ printing and then transporting that back to Earth and doing things sort of at time scales and then at sort of precision scales that we couldn't in the past. And so I think
Maybe.
there's
My problem here is that maybe you can grow organs really well in space, but transporting them down to Earth, now you shake them quite badly. Getting stuff down to the Earth is quite often a very tough problem. Microgravity is probably great for crystal growth, but it might be that it's just cheaper to do something clever down on Earth. So I think the real advantage of space is the literal space. You can get enormous distances, which means that disasters are unlikely to hit you. If some part of a facility blows up and the other parts are thousands of kilometers away, they're way more safe. I think many of the things that we regard as problems with space are the actual values. Cheap, ultra high vacuum, for example. That's golden. That's really useful. You can get a much better vacuum in space than you can get with ever so much effort in a lab down on Earth. But the downside is that you also get that getting rid of waste heat is super hard. Here on Earth, your chip fab might have struggled to make a good vacuum, but getting rid of extra heat, well, you put a few cooling towers on this roof and you're done. In space, you need these big radiators that are very ineffective if you're not running a very hot lab.
Yeah. I think this is I think one of the main reasons I have tremendous respect for people working in the space industry, especially today, because unlike the past, it's no longer a science project, right? There's a need to make things economically feasible, um, and do so to have the competitive advantage. So it's no longer sort of a choice in many ways. So I find that interesting. You had a paper called Dissolving the Fermi Paradox, which comes to a pretty bleak conclusion. Do you mind
You think
explaining
so?
a little bit, a little bit? Do you mind explaining
Mm.
some of the sort of reasons behind that?
Yeah, so the Fermi paradox is this where are they question. Where the universe is big and old, and there should be a lot of sites where intelligent life could emerge. So why aren't we seeing a lot of it? And there is this tension that makes people say it's a paradox. There should be a lot of aliens out there, and there aren't. But of course, a lot of the work here is being done by that probability you put in. There is some probability that intelligence emerges in a given site in the universe. And people usually don't go for small enough probabilities. Most probabilities we reason about are above 1 in a million. And 1 in a million times many quadrillions of places should produce a big number. what we argue in this paper is, of course, actually, if you try to have an uncertainty distribution, instead of just using random numbers you picked up from your beliefs, but actually thinking about what is the highest and lowest probabilities, then it's not that weird to see an empty universe. Because even if you take on an average a very optimistic view, think that on average there should be maybe 1 million civilizations in the Milky Way, you might still end up with a 1 in 3 chance that we're alone in the visible universe. Basically, it's our uncertainty that is making the empty sky much less threatening. This is good news because we have good reasons to be worried about the great filter. So when you try to estimate the risk of humanity getting killed by an existential risk, you can do the inside view of trying to estimate nuclear war risk, asteroids, pandemics, AI, etc. It's hard, but you end up with some numbers. You can, for example, look at what Toby Orr does in The Precipice. It's a great effort of making this rough estimate, and we can quibble endlessly about them, but it's a good inside perspective. You can also look out at the universe and say, well, we know that there is some risk for intelligent life not to come about or get wiped out. So can we tell something from the sky? And we see an empty sky, which seems to hint that either life or intelligence is really rare or it gets wiped out with a very high probability. That's very scary. What we argue in this paper is that actually this broad uncertainty range we're getting makes that sky much less scary. When we look up and notice no aliens, our update on our own chances is pretty minor, which is kind of good news. If we instead saw a lot of ruined alien civilizations and none alive, we would know that life and intelligence is likely and it tends to get wiped out. We should downgrade our own chances and probably go to the pub and celebrate our remaining years or something. But now instead, if we fail it, it's probably up to us, and it's our problem whether we become a successful civilization or not. It's not like our future is foretold in the stars.
Right. So is it a lot is your understanding very similar to I think Robin Hansen's sort of grabby alien hypothesis where, there might be lots out there, but it's so possibility wise, it's so impractical that they would have reached here, given the
No,
amount of
not
time we've
really.
had.
So this is a paper that's earlier than Robin, and in some sense he's building on what we did, but
Okay.
actually combines the reason from a few other papers. I'm kind of always kicking myself when I see that paper because I could have had that idea and I didn't. I had all the pieces literally lying around on my desk, and I didn't see that you could link it. But in Robin's argument, intelligent life that spreads across the universe is pretty rare. It's not super common. How do we know it's not super common? Well, then it would have already been here, or we would have been a very early civilization. We would not have been 13.7 billion years into the history of the universe, but in some of the earliest galaxies, because if there is a lot of civilization, they quickly spread and take over everything. So being an uncontacted civilization means that you're very early. And his argument is basically that we can know that the rate of civilization emergence can't be super high. It also might be that it's very, very low. But he also has this argument about hard steps in evolution, which I also written papers about. And then that means that he can get some rough estimate of where we are relative to that. So you end up with an estimation that, oh yes, the nearest civilization is going to be here within 1 billion years. Which on one hand, from a cosmological standpoint is, oh, that's right now. On another human perspective, 1 billion years, kind of 1 billion years ago, Earth was frozen over and the most complex organisms were blue-green algae, kind of. But we're in that scenario, we are kind of close to the transition from a universe that's largely empty to a universe that's mostly settled by intelligence doing whatever intelligence does to it. So I really like this paper. It's an interesting one because it also predicts that there is a new cosmological era that is kind of about to dawn. And we'll see in 1 billion years. I want to stay around for long enough to see whether this is correct. And maybe I get to tell Robin in 10 billion years. So, Robin, what do you think went wrong with your paper?
Right. For that to happen, we need to build the mind emulations that allow us to store our consciousness. So hopefully we get there
Totally,
quick enough.
totally. I want to have that. I don't want to be a patient zero. I want to be the guy with a clipboard asking patient zero, so how do you feel, sir? And then hopefully be patient 100 or 1,000 or something. Once the technology works and you kind of have ironed out all the wrinkles.
And I want to be the 1000th test case in some sense. So that's awesome. So getting to some more sort of recent work, we've sort of both been alive for the invention of some of these large language models. We've seen these parameters, scale up to about I think now trillion five with GPT-4. I'm wondering how you think some of those things interplay with some of your work on sort of brain emulations, and if there's any sort of tangents between the two.
So when we did the 2008 roadmap, after that there was this debate inside our institute about should we pursue brain emulation more. And there was an argument Nick Bostrom and others made that actually it might be a bad thing. We're starting to get worried about AI safety. And it might be possible to get AI safety for entirely artificial brains. But if you take actual brains and scan them, if you get just a copy of the original person, hooray, now it's as aligned as the person was, and we know roughly how to align people, and maybe we can find a bunch of saints to volunteer, etc. But there is a risk that you get something humanish, as Nick put it, something that's human-like enough that it's intelligent, you get software intelligence, but it's not actually a human. It's not actually thinking and feeling like we do. So you actually get something that's hard to align because it's just as opaque and incomprehensible as the brain is, but we don't have any handle on it. So for a long while, there was this argument that we shouldn't be pursuing brain emulation. But then we ended up with the large language models and actually a lot of other deep learning, which are basically that. We're having these opaque, complicated networks that we're only now starting to get a bit of mechanical interpretability of. And in general, they are very hard to understand. And that is very scary because they're also hard to kind of align. It turned out to be much trickier to get them to behave themselves than expected. So the hope back in the 2010 was probably, okay, maybe it's a bit like good old-fashioned AI. You just put in the right rules, although it can't be the rules. You need to learn how to be friendly or something else. So now the perspective has shifted a bit. Many people in brain emulation are saying this might be a possible last-ditch effort to get computer-readable humans into the loop. So you actually get human values that can be understood by AI, or indeed getting software people that can do some of the job like AI. At the same time, the language models and the successes of machine learning are hinting that maybe we can actually do a fair bit of a brain emulation using these other tools. Most obviously, maybe you can do some of the research using an AI instead of having a lot of expensive and slow scientists that want to go home to their families in the night. Here, we could have a lab that is doing a lot of tedious research, and you might be able to use machine learning to patch things that are hard to estimate and actually make models that run. Indeed, there is some debate about whether you could do a lo-fi approach to brain emulation, where you take a lot of behavioral data and maybe simple brain scans and electroencephalograms and emails and whatever, and try to train a model, and it's constrained enough that maybe it converges and groks the original brain. I'm not optimistic that that can work. I think we have way too many degrees of freedom inside our brain that it's actually hard to get it to work. But then again, weird things happen when you scale stuff up, and it definitely is worth trying. Maybe it turns out that we can actually grok fruit flies and make fruit fly emulations using these machine learning methods. So it's worth investigating, even though I'm more in favor of what I call high-five methods, where you actually try to scan the connectome and run it. I think these things complement each other rather nicely.
Absolutely. I think I was just going to say exactly what you said at the end, which is these things probably do complement each other in pretty significant ways, more than likely. And it could be that, in many ways we still haven't arrived at the sort of hi-fi, the ability to develop some of the technology that would aid us in terms of imaging for sort of the high fidelity things, but we can play in this territory of sort of, stupid 1.5 trillion parameter models that sometimes generate nonsense. Um, but it's a wonderful linguistic mapping. And I think a lot of these, in some sense, are NLP methods that have existed for a decade that have just been scaled up in many ways after the sort of attention is all you need paper coming out. But just moving sort of paths a little bit, you've written a book that came out in October. Um, that's correct, Grand Futures, earlier this
Well, it's
year.
not out yet. It's probably going
Is
to
it
be a
not?
long while before. No. So
Okay.
here is the funny thing. I'm writing a book about law, AI, and Leviathan. So that is the thing that hopefully gets finished this August, and then hopefully Stockholm University Press quickly prints it out, and there is no error whatsoever. We'll see about that. But my big project, and this is a multi-year project, that's why it's probably going to be out some October. But this is about what we can say about the very long-term future. Because I think the near term is very hard to predict. There are many constraints of the long term that actually allows us to say useful things about it. The astrophysics of the far future is relatively clear-cut, give or take some uncertainty about dark matter and dark energy, etc. We can say some things about the ultimate technological limitations of any species based on well-understood physical laws. And then that allows us to say some things about where the ultimate limits might lie. And then that leads to cool questions about, okay, so what do we want to do within these limits? What is the best thing we can aspire to?
Yeah. I mean, it's sort of primarily focusing on some of these more cosmic questions, right?
I
I think
start
it's
out
that.
by thinking about post-scarcity societies on Earth, just how materially unlimited can we be? So that both gets into questions like nanotechnology and energy production, but also interesting questions like what are the limits to happiness, which is probably what we really want to achieve rather than just having a lot of gold bars. We might want AI to solve the problem of automation and getting services. Beyond that, we have questions like how long can we survive on Earth? After all, if we manage to master existential risk, we can be around for a very long time. So what is Earth going to be like in 250 million years or a billion years? How do you extend the lifespan of the biosphere as the sun starts to turn into a red giant? Then I look at settling the solar system, building Dyson spheres, settling the galaxy, settling the universe. And then the fundamental questions like how much computation can we do? What are the limits to what can be computed? And given the resources that seem to exist in the universe, what can we get? And are there things that are interesting and important but we can never achieve? So I'm trying to outline a little bit of that borderland, including where we're uncertain about it. So I have a very extensive chapter about ways we could be really wrong about physics and our chances, and trying to see some of those options. What if there was faster than light transport, for example? Turns out that that implies time travel too. So you get a very crazy universe.
Yeah, I mean, I guess that's putting it mildly. I mean, it's weird. It's hard for me because there's all these things that you're quite well versed in that absolutely spark my interest. That we go down a thousand tangents. So I'm trying to think of,
Yeah.
things that are most optimal. But so just to touch on a little bit, coming to the end a little bit, what what you think some of the more useful things for younger people in their 20s, what you would have done if if you were in your 20s in this era, sort of that would keep them well positioned for a future might be. What would your advice to a younger you be,
You
basically?
want to learn a few of the kind of core disciplines or core sciences that are useful for a bit of everything. So mathematics is obviously great because you can use it for so much. And inside mathematics, if you learn statistics, yeah, super valuable because you can use that to reason, you can use that for machine learning, you can use that for statistics. Similarly, economics, which is a field I'm rather weak in. I never really got a knack of studying economics. I find it somewhat baffling. But since economic thought is fundamental for so much going on, you want to understand that. Similarly, evolutionary processes, understanding that, not just in the biological sense, but evolutionary processes in artificial life and other domains. Again, there is something that shows up a bit everywhere. So if you learn these things well, or at least have a passing acquaintance with them, you're much better able to then handle whatever else you get interested in. There are some disciplines that act as scaffoldings. History, for example, is great. If you have a sense of history, you can figure out where things fit in. It's easier to memorize information, and it's also kind of entertaining. So you might want to find a few of these core general fields that are not just about one thing, but about many, many different things. Scaffolding fields that help you orient yourself. And then, of course, just those things that fill you with energy. The problem I often find is that university courses are oriented towards stuff that's important to learn or fashionable to learn or give you a high paying job to learn. That's good. But the thing I learned the most from were these projects I did for role-playing games where I really wanted to make a proper map of Mars, and I had to learn how to download the proper topographic data from NASA and then interpret that in a map-making program. I learned so much useful stuff about that. And later on, I learned a ridiculous amount of Martian geography and other things. The amount of learning I got out of that was way beyond just a normal university course. And this was a hobby project. So when you find those hobby projects that fill you with energy, make sure you use them to learn as much as possible and link it up to other people and other fields.
Right. Incredibly important. Thank you for that. I think, one of the other things that young people get stuck in today is this sort of mimetic nature, this need to sort of fall in line with everybody else. And it could be that a lot of the future, and a lot of the sort of qualities that would be required today for the future that's coming require people to be a little bit odd, a little bit weird in certain situations, a little non-consensus when needed. What are some of the tools you've used in clearly given the sort of range of things you've explored? You have some tools. What are the tools you've used in saying, I just don't believe what the consensus is saying about this thing. I'm gonna follow a different path.
Yeah, so part of it is of course self-confidence, especially once you write about something and you realize everybody else were wrong about it and you actually figured it out on your own. You get very smug and happy. The problem is quite a lot of people then start thinking that we're always right. And one of the most important lessons I had from being around academics for a long time is to realize that very smart professors are wrong about stuff all the time. They, even stuff they really ought to be able to in an instant figure out that that can't be true. They choose to believe in the thing, sometimes because it's nice and convenient, sometimes because everybody else says so, but quite often for their own crazy reasons that everybody else will tell them is crazy, and they respond, I'm the smart professor here, I know what I'm doing. That's usually a bad sign. So being intellectually humble is actually quite valuable. That doesn't mean you want people to run over you. So you want this balance between being confident but not overconfident. You want to be intellectually humble so you learn things and check things, but also realize that sometimes you need to have an intellectual backbone. And I think you want to have a bit of flexibility. I met people who decided, I don't care about social signaling. I don't care about what other people think. I'm going to be contrarian. And then they go off and they are really annoying people. Nobody wants to work with them because, yeah, they might be right about a few things, but they're not nice to be around. On the other hand, you don't want to go the opposite direction, always agreeing with everybody else, because pushovers are quite annoying too. You want to do this balance. And that is a dynamic balance. Sometimes you just smile and nod. And sometimes you actually have to yell at people. And this takes time, and it's a skill. It's a skill you can train. When I was growing up, I read a lot of self-help books, and one of the most interesting one was Power as a Hobby by Turnus Turnerson. I don't know whether it's been translated into English, but it's basically a very cynical self-help book about how to gain power. But he's also telling a lot of truths about how you manipulate each other in family and in a company and in society, and making this observation that, yeah, even if you don't want to be manipulating your family, it's useful to know the tools so you don't get manipulated. Or you can actually choose to allow yourself to be manipulated. Sometimes you realize what's going on, but you just smile and decide, okay, I'm going to keep the peace here because it's actually worth it. Now you're kind of conscious of what's going on. These things he points out are skills. It's something you train. It's something you do. It's not something that you're just magically born with. There's some people who are very social, but most of us, we need to work on it. We need to work on our empathy. We need to work on resisting having people tugging at our heartstrings at the wrong moment. And we need to learn sometimes when we should shed a tear and actually be moved and actually help them.
Incredibly important, and I couldn't agree more. So you've lived a pretty incredible life, a long career, done some really amazing things. What are some of the core values you've carried along with you throughout that time? that you think would be values that others would be well served with?
Uh, I think my main core value is being curious. I'm curious. I want to find out what's going on, and I'm optimistic. I think there is a chance that I will find out. Many people would say, but there are things that are incomprehensible that nobody can understand. And my response is, yeah, but we don't know which of these things are like that. And being optimistic gives me energy. And I think that is a very important part too. You are curious, you're self-motivated, and yes, bad things happen sometimes. Sometimes the world is horrifying, but then you need to kind of decide, okay, I'm gonna get out of the way of that trouble and try to fix things. Because in the end, when you're feeling down, either you can fix what is making you feel down, and then you should do that, or it's just a feeling. And then there is no need to actually feel bad. You can actually let go of that feeling and move on.
Incredible. I mean, you do imbue a lot of those values, even from a short conversation like this. It's quite easy to tell. So my final question and the question that I'd like to ask all my guests is, what in your mind is the most valuable idea on planet Earth right now?
Oh, that is a good one. I think it is something like gradient descent. That is, there are many things that you can improve. And if you have a way of measuring how good something is, and you try things, you can find a rough direction of improvement. This doesn't always work for all problems. There are some problems that are impossible to get out of, but there are a surprising number of them that can be fixed. And it's a very powerful tool, especially in machine learning, obviously, but also in improving one's life. Try things, see what works, try to see the pattern, and then you can use that pattern to direct what you're doing.
Professor, it's an amazing idea. I should say I asked that partly because I've been trying to work over the last couple of years at sort of seeing if there's better ways in which we can identify the most valuable ideas and distribute them. I should say it's incredible. It's been an honor to sit and have a conversation with you. You're an amazing role model, somebody that I look up to, and I'm sure many other people do. Please keep doing what you're doing. Uh, Thank
Thank
you for
you.
coming on.
Thank you. This has been so much fun.
Awesome. Thank you, sir.